Okay, so I'll go straight to business. So the questions which I want to raise in this talk are what we can learn from the data which we measure with SNOM. Okay? And I will start with sort of describing two different classes of applications of s-SNOM. And generally, you can say that one class is essentially material science. Okay? And the point here is to measure local properties of the material. Right? So the second class is, you can call it photonics, or people call it plasmonics, depending on what exactly the phenomenon is. But the point here is the mapping of the field, local field mapping, right? So if you have some kind of waveguide structure, you can actually get the idea of what the field is created by the structure. So I'll start with this, with the material science first, and go a little bit back to what I said yesterday, what we actually measure in s-SNOM and how s-SNOM works. So in this case, we have a tip and we have the external illumination. So this illumination polarizes the tip, right? So and polarization is often described in terms of the dipole moment. So it creates a dipole here. And because it's a dipole, at the end, we have actually a hotspot, right? So this hotspot probes the sample, yeah, it interacts with the sample, and contributes to an additional polarization in the tip, which is because of the interaction. And this is what is very important, and this is what we want to detect in s-SNOM. Yeah? Of course, both of these dipoles radiate. This one contributes, let's say, to background. This one contributes to the near field, and so on. Yeah? So the properties of the sample, in this case, are encoded in this dipole. Yeah? And how do we describe this interaction? Yeah? So I didn't put any models in. I tried to stay at a very simple level. Yeah? And it can be shown that essentially this dipole, which then relates to the scattered field, is proportional to the so-called quasi-static reflection coefficient from the sample. You can think of it as being the reflection of the evanescent waves. So we have a tip which creates strongly localized waves, not propagating waves, but the ones which are exponentially decaying away. Yeah? And for each of those waves, there is a reflection coefficient. Yeah? And this reflection coefficient, we call it beta, sometimes also known as surface response function. It relates directly to the optical properties of the materials through the dielectric constant of the material. Okay? This dielectric constant is essentially, let's say, convenient quantity which describes both the reflection and the absorption in the sample. No? So it can be related to the index of refraction and the attenuation coefficient. Right? Okay, but the point here is that s-SNOM essentially measures the near field reflection from the sample. All right, now one case which is specific to materials like polymers, biomaterials, and so on. So those are molecular oscillators, so meaning that you have vibrations of the molecules, individual molecules in the sample. Yeah? And well, strictly speaking, vibrations, individual vibrations, they're not very strong. And that means that the reflection from such material is not too strong. Not too strong meaning that this beta is typically below 1 in magnitude. Yeah? So, and it can be shown that for such materials, the imaginary part of the scattered field relates directly to the absorption, yeah? And the magnitude of the reflection relates essentially to the reflectivity of the sample. Yeah? As simple as that. And this is exactly the reason why we can directly compare in nano-FTIR the nano-FTIR absorption spectra to the absorption database, so far-field databases. So we have a very good correspondence between the peak position, strength, shape, yeah? And the same is true for the reflectivity. You can directly compare the features in the far-field reflectivity spectrum of the material to the near-field reflection spectrum. Make sense? And by the way, I wanted to point out that this comparison and the correlation, let's say, which allows the identification of materials at nano-scale, can be done without modeling. So it's a direct one-to-one mapping of the peaks, which is very important. Okay. This is an example which I showed yesterday, which demonstrates how this identification can be done. So take a spectrum here, take a spectrum there, ta-dam, you know that this is PDMS, this is, this is PDMS, this is PMMA. This is another example which is kind of more relevant for biology, I guess. So here, this is a topography of a sample which has two different, let's say, biological specimen there. So one of them is actually insulin fibrils, the second one is TMV, but if you look at the topography, they look more or less the same in size, in height, and so on. Yeah? So what you can extract by doing the spectroscopy or even imaging in this case, you can actually differentiate these particles by their absorption. Yeah? You can take the spectra and you can do the amide spectroscopy and see actually the contribution from the beta sheet, alpha helix, and identify these two sample specimen. So in other words, you can also extract the secondary structure of the material, of the biomaterial, using sSNOM. Here is something which I wanted to address. So you probably heard that, well, let's say, there is, I told you that phase is related to the absorption. Yeah? At the same time, I've heard yesterday from one of the talks that you should take the imaginary part and compare it to absorption, right? So both of that is actually true. So both of those components, both of those quantities, the imaginary part and the phase, they actually relate to absorption. Yeah? The question is, what is the proper way of comparing this, let's say, data which you measure from nano-FTIR to the far-field databases? And this slide kind of clarifies this concept, clarifies these ideas. So you can see that for, well, typically in s-SNOM we're dealing with highly reflective substrates such as gold or silicon, and the sample is on top of that substrate. So in this case you can see that phase does not depend on the size. In this case it's the function of thickness. So here the points are the measurements, this is a theoretical description, the curves. Yeah, these are actually the raw spectra. So in other words, we had a polymer and we varied the thickness of the polymer and we checked what happens to the phase and to the imaginary part, which is often called nano-FTIR absorption. So we see that the phase more or less stays constant. The imaginary part actually changes. So, okay, we can say that for thin samples, when it's below, let's say 10 nanometers, so they're more or less the same. So it doesn't matter what quantity you take, you just compare it directly to the database. On the other hand, when you go to thick samples above 100 nanometers, you see that the absorption, near-field absorption, corresponds pretty well to the far-field FTIR in transmission, yeah? But not the gradient incidence, for instance. Yeah? So you have to know what to compare to what. So in other words, you have to compare apples to apples and oranges to oranges. Yeah? So, but there is no issue here. So we completely understand how this works, why the peak shifts. Yeah? So you see that there's a very good correspondence between the measurements and the theory, actually, and so on. Yeah? And on one hand, of course, I mean, you have to know what you're doing and what to compare. On the other hand, these shifts, they relate to the thickness of the material. And that gives you a hint that this shift can be used in order to derive, let's say, the subsurface structure of the sample. It can tell you how thick your material is, which is a feature, very good feature of nano-FTIR, for instance. Okay, now, there is another case. For instance, if we have materials such as boron nitride or silicon carbide and so on. So these are so-called phononic materials. So it's a collective oscillation of the crystal lattice. And of course, whenever it's collective, it's stronger. Yeah? So in this case, the reflection from the sample, this beta, could actually be above unity. So it could be stronger and bigger than 1. Yeah? In this case, you can directly relate the imaginary part of what you measure to the absorption. Okay? It's not one-to-one correspondence anymore. But you can take the spectra which you measure, reflectivity spectrum, for instance, and from that extract the characteristic resonance frequencies of the, let's say, phonon resonance or plasmon resonance, depending on what kind of material you're dealing with. Yeah? For instance, in case of plasmon resonance, you can extract carrier concentration, mobility, and so on. And this is like a quick sketch how it can be done. Yeah? So in this case, we have a material, and suppose that we have a material and we want to extract the carrier concentration. So this is what we measure, essentially. Yeah? This is how this measurement, the scattered signal, depends on the dielectric properties of the material. And this is the model to describe the electron gas in the material. So in this case, this is just a Drude model. Yeah? So there's two parameters essentially here, the plasma frequency and the attenuation constant. And both of them relate to the carrier concentration. So if we know how they're related and there's models, so I would send you to this paper where it's nicely described how things are interrelated, and it's just as simple as, well, programming, if you know how to program. And then what you get out of it is essentially the scattered signal, amplitude and phase, as a function of carrier concentration for a specific excitation wavelength, of course. So, and of course, once you do the measurement, real measurement on the sample, you can just use this plot and extract. So I know that my signal is this measured signal. Okay, so this is the corresponds to the concentration 2 times 10 to the 18th. This is a real world example how it was done actually. One of the first beautiful papers. So this is, well, this is an image taken on a semiconductor, essentially on a semiconductor structure. So this is transistor. So each of this, for instance, if we take a zoom here, so that's would be an image like this, and that corresponds to the transistor. You see, so you can identify the components like source, drain, gate in the transistor. You see that you see nothing in the topography. Of course, it was cut and polished. Yeah? So, but what you can do with this image is you take this curve. Now, this one is slightly different. So instead of plotting a signal as a function of concentration, so it's plotted as a function of frequency for specific concentrations. This is because you can do measurements at different frequencies, so you want to know these curves, yeah, for each of the frequencies. So in this case, the example is terahertz, so it's this frequency, 118 micrometers. Yeah? And you can extract the carrier concentrations depending on where you are on the sample. Yeah, and what I wanted to say here also is that this is a calibration-free method. In other words, you don't have to do much with your s-SNOM setup yourself. So with the s-SNOM setup itself, so you don't need to do the complicated calibration procedures in order to characterize the machine. So it's pretty simple, well understood. This is another example which Andy showed yesterday. So the same thing. So you can identify the carrier concentration pretty nicely using these simulated curves. Yeah? Here's another example what you can do with s-SNOM. So I already gave you a hint that s-SNOM gives you the information not just from what on what is on the surface, but it also gives you the information of what's below the surface and how deep it is. Of course, in a certain limited range, yeah, determined by the localization of the hotspot. And that means that in principle, we should be able to extract this information. And this is kind of the concept how it can be done and what data we need for this. So in this case, so this is, suppose that this is an unknown sample. We do images. We take an image on that sample. And a cool thing about s-SNOM is that because we're using this high harmonic demodulation, so we're jittering the tip and then demodulating the signal at higher frequencies of that frequency. So we can actually collect the information using several demodulation orders, several harmonics, let's say second, third, fourth, fifth, and so on, right? And it so happens that each of this harmonic gives you different information about the sample. It sort of tells you where the signal is coming from. So lower harmonics probe larger volume. So they are telling you information on what's below, what's down there. And higher harmonics, like the fifth one, is very highly localized, so it probes only the top layer. Okay? And then if you're armed with a mathematical procedure, here you would need to use the model in most cases, you can actually extract the sample structure. So you see the thickness, you see the dielectric constant, okay? And this is concept, this is the real measurements. So in this case, this concept was tested on the silicon dioxide wedge, which was on the silicon wafer. So in other words, once you scan along this silicon dioxide wedge, so you see that different harmonics indeed are not the same, so you have different contrast, so different trends, but you don't know whether it's related to the thickness of the material, whether it relates to the permittivity of the material, and so on. So, but you can do the reconstruction procedure and actually recover the thickness of the silicon dioxide layer, and you can recover the permittivity. And you can see nicely that it changes from being silicon here. So here we're measuring directly on the substrate. And then we get to the value, which is known in literature as the permittivity of silicon dioxide. Yeah? This is a combined plot which shows you the structure and encodes the permittivity in the color. All right, second class of applications, yeah, which is local field mapping. Okay, in this case, it's not the tip in most cases. Well, it can be, but in many cases, it's not the tip which is a source of excitation. But the point of having the tip is actually to map the field which is created by the structure. So we have the illumination, yeah, which excites the structure directly, creates certain distribution of the field. Let's say the hot spot here is not related to the tip anymore, but it's more related to the sample itself. And we put the tip there in such a way, I mean, the purpose of this is to get it polarized, and then it scatters to the detector. And by detecting the scattering signal, we know what is the local field at this point where we put the tip. In these cases, most of the time a dielectric tip is used. Because metallic tip is strong, it also polarizes, it creates hot spot, and that disturbs the local field. So if you want to map the field, you want to have a probe which is least disturbing for your sample, of course. Yeah? This is an example. So this is a transmission line, infrared transmission line. So essentially, it's the dipolar antenna here, which is used to, as a source of excitation, so it captures the incident light. And then this light actually propagates along the structure. There's a very small gap here on a scale of 10 nanometers. And we can use s-SNOM, and we can map the field in this structure. And you can nicely see that you have an antenna which is excited. Once again, you see this hot spot. It's just like it being a tip. Yeah? So the tip polarizes, creates the hot spot. In this case, it's antenna which polarizes, and it has two hot spots on each end. Yeah? You have the wave. Yeah? And because we're detecting phase, we don't just get the magnitude, but we also get the phase information. And why? So yesterday there was a question, why phase is important? What does it show you? So in this particular case, let's look at this image. So suppose we only measure the amplitude. Yeah? What can we learn about the propagation in this antenna, in this transmission line? Decay. Yeah, we see that the field decays. Okay, so we can characterize the decay. But once we have the phase, we can plot, for instance, the real part of field. And you see that it's not just the decay, but you can identify the wavelength of light. Yeah, so the period essentially. Yeah? You can identify that this is now a clear dipolar pattern, so it's like opposite charges, yeah, plus minus, opposite phases. You can characterize the mode structure in the transmission line. So it gives you another layer of a level of knowledge about the propagation in your structure. Okay, and this is essentially my last example. So this is molybdenum diselenide, and what I'm trying to show with this slide is that s-SNOM can characterize one more very important characteristic of optical excitations and materials, and it's called dispersion. Dispersion relates the energy and the momentum, yeah, and it's one of the fundamental characteristics for deriving optical properties of materials. So in this case, we have an interface between, well, essentially it's a molybdenum diselenide flake on the substrate. And what we see here, if we do imaging, we see the fringes. These fringes come from the fact that once we place the tip here, it launches a wave which goes here, comes back, okay? In other words, we see the interference pattern between the wave which is launched and is coming back. Yeah? So these fringes can be imaged, or well, the period in these fringes can be measured for different frequencies. We can tune the laser, for instance. So in other words, you see that we have the fringes, yeah, we have the different period, yeah. But the period relates to the wavelength. The wavelength is essentially reciprocal of the momentum, okay? So this period, if we do the Fourier transform, directly gives us the momentum of the excitation. Yeah? We know the energy of the excitation because we illuminate with a specific frequency of light, and we can get the momentum. And once we just plotted these dots, this is the dispersion. This is the dispersion of the polariton excitation in molybdenum disulfide. Yeah? And the color here, this is the simulation, and you can see that it nicely fits actually to the theoretical expectations. That brings me to the end, to the conclusions of my talk. So hope that I convinced you that s-SNOM can deliver chemical information, conformation, and local doping. Yeah? Hopefully I also convinced you that it's a quantitative tool capable of subsurface imaging, and it fully characterizes optical excitations in 2D materials. Thank you.